Okay, welcome back, everyone. So as I mentioned, we're going to begin now. And feel free to ask any questions. The first part, as I mentioned, it's more like evolution of rubber elasticity theory. And if everyone recall, we made a few assumptions in the last class. Those simple assumptions give us a very unique capability, actually allow you to see when you stretch a rubber, how much force you can expect when you stretch it twice or 3, 4 times because of loss of entropy, okay? And the assumptions are we do affine networks. So macroscopically, how much you pull it will match what microscopically. And we assume also entropic changes little, but apparently some of the assumption may not be met in real conditions. We will visit why, and we will explain some of the revision people did to our current series to make it a little bit more realistic. It's still not going to match everything because there's a lot of factor coming into play, but at least it will make the series more realistic. So let's go through that.
Loss of entropy to translate to rubber elasticity force. Okay, we were able to discuss the lecture and understand how we can predict the stress as well as modulus based on number of entanglements or entanglements between molecular weights. So this is where we were left, and this is a part of the important lecture where we discuss what is a G in terms of modulus depends on cross-link molecular weight Mx, or you can understand this is a number of cross-link points within a given volume. So in other words, we know the theory nicely described if the temperature increases or cross-link density increases, your modulus or your strands of the rubber is getting stronger. Okay? So what we're going to do in today's lecture. So today's lecture is slightly different with what we talked about before. I want to go back to the slide where we talked about a few assumptions for rubber elasticity theory. We discussed that this is going to be a finite network, and the initial network is isotropic and volume constant driven deformation. So this first one is true at a low degree of strain. So if you imagine if you stretch a chain, at the initial stage it will be Gaussian flow, but if you stretch the rubber a lot and assume it's 4 or 5 times difference with what your initial length, then your coil is no longer a Gaussian coil, and it's a very much elongated coil, and your value will be different and depends on degree of strain. So the first assumption does not hold very well in high degree of strain for rubber material, and we will see why that's the case, and we will discuss what the results look like in today's lecture. And the second part is where we discuss where the initial network is isotropic. So this is usually hold true, and in many cases where your rubber is going to start with isotropic state. The volume remain constant, and that's pretty much the case. But again, there's always going to be a deviation from ideal Poisson ratio of 0.5 or ideal elastoma. So based on the theory we had, people were able to do an example test where you get a rubber, you plot tensor or compression force with respect to compressional extension, and you were able to see how there's a mechanical response of the material. And you can tell the theoretical curve is showing the solid line, while the dashed line linked by between the dots are the way people discuss about those material, and you can tell it is pretty much a good agreement between your theory and your data. But if you watch carefully in the compression region, it is very good. However, in the tensor region, or extension region, your data data start to deviate more and more with a higher degree of strain. So look at here. When your strain is 2.0, it is much bigger difference. This is especially true when you stretch a rubber at very high strain. So look at here where you have the extension ratio. It's basically draw ratio from 1 to 8. And the higher the extension ratio, 8 means we deform the rubber 8 times of original length. So 8 is very high value in terms of deformability. And you can see the theory is what when we discussed the entropy theory, predicted that your behavior will behave like this. But in reality, if you can count, I would call maybe between 1 to 5 degree of strain, it's pretty much similar, and there is some deviation, but not terribly bad. But once your strain is above 5, your rubber elasticity deviates dramatically with the theory, and this is what you see. It can be up to 100% differences between theory predict the force per unit area will be about 3.0, while the reality, if you measure it, is already exceeding 6. That's a big difference. We discussed this is pretty much due to the Gaussian coil assumption. Gaussian coil assumption is
Siri is making fun of me.
When RE is close to LC, right? The second is the strain-induced crystallization can be happen. So the first one is easy to understand.
So the second problem, I want to mention a few words on strain-induced crystallization. This we don't consider in our theory at all. In the model we developed in the last class, when we stretch it, we say you only have entropy difference when you stretch it, right? That is pretty much true at low strain, and you will learn one of the uniqueness for many rubber material is they could have something called strain-induced crystallization. And crystallization is a concept you probably haven't heard because it will be covered in the solid state property next semester in greater detail. But briefly speaking, crystallization is when your chain is able to align in a perfect lattice. They will form something called a crystalline region. And that typically happens at low temperature, at the crystallization temperature, okay? So temperature plays a big role on the crystallization. You can see when the water is below 0 degrees Celsius, it crystallizes. And once crystallized, it changes many properties, modulus, and many other. So when the polymer crystallizes, the crystal regions are higher in density, as well as higher in mechanical response. So rubber is interesting because its TGTM is much lower than room temperature. So at room temperature, if it's not cross-linked, many rubber are viscous liquids. So you have to cross-link them to make them not flow. Otherwise, it will show something like creep. You draw it, and it just flows away. Okay, it will not be able to maintain shape. That's why we cross-link them. But it won't crystallize room temperature because the melting point is below room temperature. At room temperature, everything crystal melts. However, once you draw it, you will create a special phenomenon called strain-induced crystallization. And because when you stretch it, its chains are aligned, and because of this alignment effect, you have a chance to make the polymer crystallize while you stretch it. Once you let it go, the crystallization just melts. So as you can see, when it's crystallized, it will have a strong deviation. So crystallize, I think, happens roughly about here. And low degree crystallization, it doesn't make a huge impact, but the more you stretch, the higher the crystallization is, and you will have deviation. So the Gaussian coil rubber elasticity theory, don't consider that. That's one of the major reasons you lose theory versus the reality in high degree of strain.
Second one is what happens when you have a rubber material. A lot of times the rubber shows very unique properties because it has strain-induced crystallization. So what this term means is when you stretch a rubber, in a normal case, crystallization happens when you change the temperature. If you heat and cool, when you cool the material down to its crystallization temperature, your material starts to crystallize, and you see you would start to see changes in the degree of crystallinity. But additionally, the strain can also induce crystallization. If you stretch a polymer, if it's above a certain threshold, it will start to crystallize. And this is what people call strain-induced crystallization. Okay? This crystallization happens to act as a physical crosslink. And it's not a covalent crosslink, but it's something similar. It's called a physical crosslink, where the crystallized points basically act as a crystalline points. And as you can see, if we happen to have physical crosslink points between those covalent crosslink points, then you would have artificially increased crystalline density. This would result in an increase of the modulus of your material. As this is partially the reason of why this will have a rapid increase, a lot of crystallization happens here. Meantime, there is a lot of deviation from Gaussian series, so this is something you should keep in mind when you use this theory. Now the question is, how do we address this? How do we solve this problem? Don't make it happen. And there's a couple researchers developed several theories, so we're going to talk about a couple developments after the Florentines and others developed their entropic rubber elasticity theory. So a couple of assumptions, and there is no changes in the internal energy at constant temperature P and U, and there is no change in volume at T and P. And this is one of the reasons we can link the delta, the force to partial derivative of the delta G to displacement L. And this has been discussed quite nicely, right? So Gaussian core deformation distribution, we talked about it, and it's likely need a fix up because it's not going to work out. Chain conformation before the deformation is the same as chain conformation on crosslink states. So this is going to be related to another theory, how we can address what the conformation change before and after. This is also important because if the crosslink influence the morphology, then it will impact our theory. But most of the time, it's not a big effect, not as big as the assumption 3. Okay? And junction point affine to the macroscopic deformation. So as we talked about, when you stretch a rubber material, your crosslink point will deform with macroscopically. This is not always true. Deformation is sometimes inhomogeneous in the local scale. So some point might deform slightly bigger than the other. So this causes modification needed to understand how to address this affine deformation. Last is a number of elasticity effective strain per unit volume is given by this. This is pretty much easy to fix, and this is all we need to do is to get a real effective strain. Okay, not just apparent effective. You can back calculate based on modulus to what is effective by. So first is let's see what the assumption we can do. Chain conformation for the strain follows Gaussian distribution. As I mentioned, this is one of the big reasons we need to address this. And this was done by adding an inverse Langevin function. This is done by Jung. So this approach is slightly different, where people added an additional term to count for non-Gaussian behavior. Okay? So if you look at the force, inverse relationship, if you plot 1 divided by x, and you will see if this is the value, then inverse relationship will show this particular shape of the response, and that will, ideally match this part. But if you only keep this piece, then your low deformation region cannot be captured. So a smart way is to combine the conventional approach where we add, and as well as adding two additional terms to this inverse Langevin function to capture those non-ideal Gaussian coil deformation. Okay, so this is basically what people showed in the probability of the distribution of chain and function P dependence of nx and h. The other one is regarding the idealized chain network. This assumption says before deformation is the same as after deformation. And this one is just a need to introduce a conceptual frontal factor, because crosslink might slightly change the chain conformation. So what people did is to slightly modify what is h value. So added hi and h0, and these two factors, hi is after crosslink, h0 is before the crosslink. So this accounts in slightly difference in the end-to-end distance change. As you can see, this does not affect the overall shape, but it will modify what is initially the shape of the original stress strain curve. Okay. And the other one is a fine deformation. A fine deformation discusses how the deformment will deform finely to the macroscopically. This is to introduce an idea of phantom network to lower the effective number of crosslinks. Phantom network, what does phantom mean? Phantom means something is not real, something is idealized. Like phantom opera is something not ghost-like. Okay, so this ghost-like network is basically the people address the way how you can attribute to the fine network limitation. Ghost network means we put a black close to what the network is. We don't care, or we don't want to understand in every single detail where the network crosslink point is. But we instead introduce this ghost term, and this ghost term has a unique ability to say that you have a network crosslink point. This crosslink point is somewhere in that area, and it will stay there. And using this ghost network, it will allow you to capture the deformation should be affine to macroscopically. Okay, so this is again a minor modification to address this prefactor term. In VE and VX, VE is crosslink density. VX is a consideration of after we crosslink, okay? Or after we modify this phantom network, what is phantom network's influence or correction factor? So VE minus VX will be the real crosslink density, while the VE was originally the crosslink density without accounting the phantom network. Okay? So this network will basically, there is also people start a term call it a network. They can imagine also would it behave like a chain would have fluctuated around its ideal mean position. So it's, in other words, let me get my pen. In other words, phantom network basically says you are no longer fixed at here. This crosslink point could fluctuate within this sphere. And within this sphere allow you to slightly modify the crosslink density. So that's a difference between the two. There's one more modification we need to do is effective of the strain on that unique network is given by this rho, also Avogadro constant, divided by nx. Nx is a crosslink, a molecular weight brought between the crosslink points. So there is also need to consider there's defect in the crosslink, and there's trapped entanglement between the partner chain. So what this means is if you have crosslink points, they only passes 2 p's, and they're not crosslink again. It's a network. So it's like a dangling loops. And this needs to be considered as a way to modify it by using another parameter called ME. ME is where we consider this modified entanglement density in addition to MX. So this is what the original term. This is the additional piece of fitting parameter. So this fitting parameter will allow one to capture better cross-link density within the network. Okay? So combining everything together, the most popular rubber elasticity theory modification is called Moody Wriggling equation. So what this does is where people add, this is original term where we get stress is dependence on a constant prefactor and lambda minus 1 divided by lambda squared. And what Moody, based on the continuum argument, is we can add a second continuum term, C2, and its dependence on extension ratio is weaker, so it's no longer dependent on lambda, but dependent on 1 divided by lambda 3. So, okay? And by combining these two, we can see we can now modify the original equation to have C1 and C2 term. And C1 and C2 are two constants, and you can get the C1 C2 based on measurements. So how do we get the C1 and C2? C1 and C2 are two constants, and the way we get it is basically based upon measurement of stress and strain. So we can measure the stress, we can measure the strain, but now instead of plot with stress versus strain, we need to modify the stress with stress divided by lambda minus 1 divided by lambda squared. So this is a new y value, and you can plot against this 1 divided by lambda. This will be x. So again, I'm going to ask you to take a look at this equation. Y equals a plus bx. So here y is basically plotted as stress divided by the strain, lambda minus 1 divided by lambda squared, and stress x is equals to 1 divided by lambda. So if you plot this way, the intercept with y-axis will give you what is a value, or C1, and the slope of this curve will give you C2. Something like our osmotic pressure and the measurement of the secondary coefficient and molecular weight, but instead here it gives you what is C1, C2. So you can extract the C1, C2 value, and this is a good empirical approach and give you a much better fitting into the experimental data in the rubber elasticity theory. Okay? With that, I think that will be end of the lecture. So the last part of the...
Okay, so let me finish it here. As you see, it's more about this quick recess of what we talked this morning is just some fix up we did to the original equation. You know, considering the defect in the network, considering when your strain is no longer, the Gaussian coil is no longer at high degree of strain. All those fix up will help you to better capture the obvious physical behavior of your rubber at high degree of extension. Okay. And it's kind of important. In many applications, you need to consider how you stretch the rubber at high extension. Application, for example, tires. Locally, your tire, when it's going through when it's hit the ground, when you step on the gas pedal, it's actually local strain is pretty high, and that's why it can respond to these. But in the end of the day, you need to understand a little bit what Moody-Wriggling equation does and how this could fix up some of the early series by looking at the simple Gaussian coil. Okay, so with that, I'm gonna finish the discussion here. Then I'm gonna verbally talk a little bit about what we have learned and what's the plan for the exam. So I need everybody interact a little bit with me for this part. So what did we learn for the first month in September? You can say a few keywords. What do you remember what we did in the first chapter?
We were learning all about how the chains exist in an ideal world.
Yeah, we learned about, if I were to put a word, everything about chain conformation. Okay? Conformation means how the chain looks like it behaves in three-dimensional space, right? I recall we begin the lecture by talking about a simple question: how large a polyethylene chain would be at 280 kilodalton at different states, a fully extant states, and that allude to contour lengths. And then we talked about end-to-end distance. I think by then, not everyone may not know what end-to-end distance, how it defines, right? So now you should know how to define end-to-end distance. And with that, we talked about several models and how we can use these idealized models to describe your chain conformation behavior, right? What are these chain models, by the way? We started with most simple one.
Freely rotating.
Free joint chain and then free rotating. You're very close. Free joint, free rotating. What's the last one? Hinder rotation, right? And we go from most ideal case where there's no single restrictions. Then we introduce a little bit more complex or more realistic terms when you can consider the angle restriction or the dihedral angle restrictions. They are very similar. I think at the end of the day, the scaling relationship, although it's a concept introduced much later, but you were able to apply it now to see all three models scale with a molecular weight of power of 0.5 for end-to-end distance with a number of bonds and relationship, right? That tells you it's idealized the chain. We always call that random walk chain, okay? So this was maybe the first week or two. We talked every single thing about how to understand polymer size, coil size, how it's related to molecular weight, how it relates to the bond angle, etc. Those are very fundamental, but it's a good setup for you to learn the rest of it. After we talked about those effects, what else we discussed in that chapter? I think there's something before that. Radius gyration, yes, that's a very important part we talked about. And we can discuss the radius gyration first. Radius gyration is something we alluded to when we measure your polymer in those idealized states. We did all kind of theory about how do we measure it, and that's where the radius gyration comes in. And radius gyration is a parameter related to end-to-end distance. You have to know how they are related. And radius gyration is a parameter we could measure by several techniques, including light scattering, which everybody haven't learned yet. They're going to be a half a chapter dedicated to use light scattering in the next spring when you guys came back. And we also talked about other tools you can measure RG, but not directly. We would be able to measure molecular weight to get osmotic pressure to get that value as well. But that's the reason we need to measure RG, and everybody should know what the definition of RG and how to calculate RG with the polymer chain and maybe even a rod-like structure. And those are important. From that, what else we learn? We know the RG, we know the end-to-end distance. Persistence length. And why we talked about persistence length is we had a trouble to describe how rigid the polymer using the end-to-end distance, right? Because this depends on how big your chain size is. So we introduced the idea of persistence length. And this will be a nice way to describe how rigid your polymers are. And we also talked about worn-like chain model. It's a different model to describe better how semi-rigid chain looks like. We also discussed another concept while we are getting to the persistence length is a characteristic ratio, right? Everybody should remember what this value it means, C infinity, and how this is related to persistence length. Characteristic ratio is another way you can understand persistence length. So what's next? I think it covers 3 weeks of that, what we want to talk about. There's only a little bit thing we talked about at the end of the first chapter. What are these? okay, it's been more challenging. We talked about everything is about, there's two assumptions. First is we talked about idealized chains. So I believe at the end we talked about how you go from idealized to be a little bit more realistic. So we go from male zeta solvent and those idealized conditions to good solvents. We chatted a little bit about how good solvents impact your conformation, and everybody should know by now, right? Good solvent induce some phenomenon called self-avoiding chain works and allow the chain to be swollen compared to the idealized condition, and that resembles a good solvent. And you should be able to tell what's a good solvent and zeta solvents, the difference are, and how you can tell one from each other. And that's actually a good connection with what we talk about solution, but we'll get into in a moment. Okay, and there's one last piece we cover, and I think is quite important to the lecture we talked about today. What is it in chain conformation we talked about? All right. Probability of the distribution, right? That's also very important because everything I talked about, the first part, or the end-to-end distance or G, is all averaged property. So we look, if you have a milling chain, the end-to-end distance average is what we chat about. RG average square will be equals to NL square divided by 6, right? But if you pick a single chain, out of those probability, it will adopt something maybe longer end-to-end distance. So we need to know what's the probability of distribution. And we use that as a way to understand what's the entropy for the chain before and after stretch. So you need to understand a little bit about probability of distribution. That's a nice summary of what we did, everything for the first month. So you need to go back and to tell a story how we can understand polymer conformation with your peers and down the road with your manager or anyone, right? So conformation is what we talked about in the first part. So in the final test, we will, again, ask everybody about conformation questions, understand chain dimension, chain size. So you should expect a question along those lines. And expectation multiple choice, defining of a definition, and maybe a numerical question related to chain dimension, okay? Or maybe RG, I could not tell you more. You should know both. So after chapter 7, all about those idealized chain, what did we do? If you use 2 keywords to summarize the next chapter, chapter 7. Come on, anyone?
Mixing solutions.
Perfect.
Polymers and things.
Yeah. Yes. We talked about phase behavior and the mixing of the polymer and thermodynamics, right? Everything is centered around the thermodynamics of the polymer solution. And instead of just looking at a chain floating vacuum in zeta condition, now we're trying to understand how polymer interact with itself and how it interact with another material such as solvents. So at the end of the day, this chapter with one single goal is help you to understand the phase behavior of the polymer, how polymer could interact with another polymer, will they mix, or will it mix with the solvents. Within that, we introduced the MVP of this class. What is that name? What a parameter we talked about? Flory-Huggins chi parameter. This is really the jargon. So if you're a polymer physicist, you need, hey buddy, what's a Flory-Huggins parameter? If they can tell you, they probably know a little bit about polymer physics. So you guys need to know what is a Flory-Huggins parameter. I call it MVP of the polymer physics community, or GOAT of our polymer physics. You have to know it. Going from a simple one, we go to a little bit more complex one. What is a more complex model, and what we modify with the simple model?
The
Yes, Flory-Hagen theory, thanks. Jeff, what we changed between the lattice theory and Flory-Hagen theory?
In a polymer, each monomer unit only occupies one space.
Yeah.
In the lattice.
In the lattice theory, you don't consider connectivity and how connectivity played a role in degree of mixing. And later we know this actually has a tremendous impact in ability for the mix, right? Although enthalpy is still going to be dependent on case by case, but your entropy, which is a big proponent for helping the polymer to mix, going to drop quite a lot because you have this connectivity comes into play. You should be able to use that to understand why it's harder to mix polymer together, okay? So what we did next, all these thermodynamics from these two nice model systems is very good for everybody to get started understand thermodynamic of mixing. So after that, what did we do?
Osmotic pressure.
We did osmotic pressure. And when you look back, it might be things strange. Why osmotic pressure? How does it relate to the phase behavior? Indeed, it may at the first glance it's a little bit interesting, but osmotic pressure helps you to understand the quality of solvents, how you can understand using the A2 parameter. And osmotic pressure is also tied into the thermodynamics because we introduced the concept of chemical potential, how chemical potential can relate to polymer solution concentration, right? All these I hope everybody can recall and study it one more time. And how we can use osmotic pressure to calculate molecular weight, quality of solvent using very concentration-dependent test. Okay. After a short detour or a stop, we come back to the same track. We look at phase behavior. Now, using the Flory-Hagen theory, we are trying to connect a very important concept of how we can use Flory-Hagen theories to predict the phase behavior if we know chi parameter. We have to know the chi parameter. If we know that, then we can easily predict a phase diagram. That means at what temperature, if you want to for one phase or two, right? If everybody recall, there is a nice relationship between the first derivative of delta G versus the concentration will tell you something, and second derivative will tell you something. When we define the critical point, for example, third derivative of delta G versus phi equals to 0 defines second defines a critical point, and the second derivative of delta G versus phi depends your binodal points. Okay, all these you need to understand, and of course those. Again, some of the concept only pertains to polymer physicists. What is binodal point? What is binodal point? What are these terms means? If I mix A and B, if I give you a chi, can we predict if they will mix or not? And all the nuts and bolts about phase behavior, you should be able to read a phase diagram and understand like other concepts like LCST, UCST are. Okay? I think that's pretty much covers the second part. If I have to put words on that, that session we reviewed quite extensively how we can apply the thermodynamics to understand the phase behavior of the polymer. Okay. Any question for that part? I think it's also quite self-explanatory for that particular section, right? Then the last chapter is also the shortest one, is what we have did in the past 2-3 weeks. We reviewed what is the rubber elasticity theory and why rubbers will be elastic, and it can be very different with a metal in the sense that how can we use the entropy loss to explain the force is being experienced by a rubber band when you pull it. And although it's a shorter section, but I think it's another very successful story about how we can apply chain conformation and second law of thermodynamics to explain a very practical problem and important problem in polymer community, okay? In this, we need to understand enthalpy and entropy's role, how they come into play for the rubber, and how we can use that to capture some of the interesting phenomena at low degree of strain and how degree of strain, why they deviate, and how people develop some ways to mitigate the problem, okay? So with that, I think I have taught everybody what I'm trying to achieve, to get an introductory course about the polymer physics for everyone. And a few suggestions how to study the final exams. My teaching philosophy is more in want to make sure everybody can still carry the knowledges a couple years after you graduate. So I will put a lot of emphasis on how you can understand these concepts and apply them. I will be a little bit lighter on numerical questions, but I want to make sure you can apply these concepts into practical use. So we will have multiple choice like we did in previous 2-3 tests, okay? And a good way to study is I would recommend everybody go back to read the polymer chemistry textbook one more time. The Professor Lodge write a very nice, simple to read textbook. It will be a little bit slightly different, but with the knowledge we taught, you should be able to understand most of it. Second one is to review some of the quizzes and homeworks we have done. And I'll post the answers to the latest one. We haven't get a chance, but I'll post a video today so everyone can watch it and see the answers for the chapter 10's homework, okay, for rubber elasticity. And with that, I think that's all you need to be successful in the last text, okay? And the test will be Tuesday. And there is a test time. I'm gonna check again on the provost website. Usually they would assign the similar time, so I would expect 9:30 in this room. And I will again have the same test, close the book, but I will offer you the equation sheet for everyone. And test is from 9:30 to 11. If you need special accommodation, I'll make sure I got that one for everybody, okay? So, any other question for me? If not, then good luck for the final week. Should be fairly straightforward. If you can follow when I discuss what we taught with you, if I mention concept, it's ring a bell for you, you should be able to pass the exam or achieve a relatively high score easily, okay? Then should you have any more concept you need to clarify, I will be